This is the last problem of the AMC exam, and number 25 tend to be the most difficult. So I'll try to make this as easy as possible, but it's going to take a while to explain fully in detail. So let's read this together. Let a is greater than 0, meaning that a has to be positive, and let px be a polynomial with integer coefficient. It's important that we have integer coefficient and we have a polynomial, and we have p1. Okay, so we are given the two lines of information, and we have to ultimately find the smallest possible value of a. Since we're given the polynomial as our subject, we'll write the polynomial equation that satisfies the first line of the equation here. So when we have px, we can set that equal to a, but I'll first write x minus 1, x minus 3, and then x minus 5 and x minus 7 times the another polynomial with integer coefficient plus a. So whenever we have x equals 1, 3, 5, or 7, we get 0 on the first term, leaving us only a to be equal to the px. We can also write this as px minus a, and this will be more convenient when we use the second equation. Now we're going to use the second equation here, p2, p4, p6, p8. So I'm going to set x equal to 2 first, and then I'm going to plug it into our rough polynomial equation. And later on, to find the smallest value of a, you will see that our px here will be more sophisticated and further expanded, and from there we can deduce that this polynomial, we can create a polynomial that can be nested within another polynomial, and find the pattern, what gives us the smallest possible value of a. So x equals 2, let's plug it in, p2 minus a, and okay, so we get negative 1, positive 1, negative 1, negative 3, negative 5. So on the right side, coefficient becomes negative 15, and then q2 equals, you're gonna get negative 2a. The reason is that p2, you see p2 there is basically negative a. So I can replace this with negative a. Negative a minus a becomes negative 2a. Moving to x equals 4, you have p, and then you just have to plug in 4 here. So when we simplify, we get 3, 1, negative 3. When you multiply out, it becomes positive 9, 2, 4. And again, we get negative 2a. Why? P4 happened to be negative a as well. So for clarity, let me erase these numbers. Alright. Okay, let's go to x equals 6. It's the same pattern all over again. So again, I'm gonna skip this. So we have negative 2a equal. Okay, it's the same method, except this time I have a 6 in the x. So you have 6 minus 1, you get 5. You get 5 minus 3, you get 6 minus 3, you get 3, 1, and negative 1, cube of 6. So when you multiply this, you get negative 15, which is the same coefficient as when x was 2. So negative 15 q6 equals negative 2a. Let's try x equals 8. Okay, again on the left side we are supposed to have negative 2a, and when you set x equals 8, you get 7 times 5 times 3 times 1 q 8. So 35 times 3, you get 105. Now it's time to deduce. Okay, take a close look at these 4 equations we just found. Okay, on the left side, everything is equal to negative 2a. But on the right side, we have 15, 9, 15, 105. And just imagine the q2, q4, q6, and q8 to be an integer. Because in the polynomial, in the direction it said the integer coefficient with integer. Let's see what it said. It said the integer coefficient. Polynomial with integer coefficient means that our q6, q4, q2, q8 must be integer as well. Therefore, what determines what's very important is something that satisfies all 4 conditions given 15, 9, and 105. The least a we can have is by finding the LCM, the least common multiple of these orange font numbers. Okay, hopefully you remember how to find the LCM. So 9, 15, 105. When you perform this, see if you can divide it by a common number. So I see 3 is a good candidate. So I can have 3 here, 5 here, and 35. As long as there's 2 present that can be further reduced, you can keep going on. And I see 5 here. That 3 has to just come down, and I have 1 and 7. When you find the LCM, you take the vertical and the horizontal at the bottom or at the edge, and you just multiply them simply. So LCM for this number becomes, actually I have that there, so I'll erase that. 3 times 3, I get 9. And then 545 times 7, you are supposed to get 315. In other words, our A can be or can have 315 as our factor. So what I mean is A can at least have 315, but not restricted to. We can also have another factor. I'll call that integer n. Okay, so looking at that, we can definitely eliminate choice A, because the least we can have is 315. So you can kind of deduce the answer has to be 315, but if you really want to know that n becomes 1, we can further expand our polynomial, meaning we right now have the px, but using these x equals 2, 4, 6, and 8, we can identify more accurately for the qx, and then expand polynomial within polynomial. And let me illustrate that. Okay, so we found that when x equals 2 and 6. Notice how we have the same coefficient, negative 15 for both cases. So we have q equals 2. Remember, we had negative 15 equals 2a. But using the LCM calculation, we were able to find the a at these factors. So now I can simply substitute these in 2a. When I further simplify, I get q2 equal, let's see, you should get 42n. So what does it tell us? When we have q2, qx, we'll have 42n when x it matches to be 2 or 6 with another polynomial. Okay, notice this is analogous equation to our px and qx, and we can substitute the qx with this more elaborate equation here. Okay, so now I'm gonna set, when I set x equals 4 and x equals 8. So let me start with 4. We use the same method. When x equals 4, we had the coefficient of positive 9. So let's find that. And remember, we just found the a to be 315 times n, so I can simply replace that. Okay, that becomes negative 630, just like one above. Now when you divide by 9, you're gonna get negative 70n. So q4 equals negative 70n. And when you have q8, let's do that first before we further expand our rx. We have 105 q8 equal negative 630n, and when you divide by 105 on both sides, you get q8 equals negative 6n. Okay. Now these are important for now, but our goal is to find the rx. Okay. Let's start with x equals 4. When we have rx, and say we put 4 here, when x equals 4, you're supposed to get negative 70n. So I'm gonna put I'm gonna put negative 70n here. Okay, before I find rx, let's plug it in. So negative 70m equal 42n plus, okay, when x equals 4, in both parentheses, you're gonna get positive 2 and you're gonna get negative 2. So in the end, you're gonna get negative 4. And then you have r. Okay, we will have r4. When you subtract 42m on both sides, you're gonna get negative 12n, and this equals to negative 4 and of negative 4 R4 and so our R4 becomes 28n. And let's do that for x equals 8. You will have 6n equal 42n plus alright, you get 6 here, you get 2 there, so 12 R8, and then when you subtract 42 on both sides, you're gonna get negative 48n. So our R8 becomes negative 4n. Using these pieces, we can deduce our Rx. So how do we do that? So we have Rx equals 28n, and when do we get 28n? When you have x equals, not x, yes, x actually, x minus 4, okay, times, okay, now I'm going to try to have a Rx with both components of x equals 4 and 8 calculations we just did earlier. Okay. When you have 8 now instead, x equals 8, and you have x equals 8 here, you get 4. We are supposed to get negative 4n. To get that, to get negative 4n, you will need 8n here. Actually negative 8n. Because, okay, let's say we put x equals 8, you get 4. 4 times negative 8, you get negative 32n. Negative 32n, and I'll try to make this equal to 0 when x equals 8. And you will get negative 4 by combining with 28n. So to achieve this polynomial, I must have x minus 8 that follows our another polynomial, and this time I'm going to set that equals to tx. You can choose whatever you want, sx or zx. Just this is another polynomial with integer coefficient. Okay, you will see this pattern already, that you have this like remainder, and then you have your quotient with another polynomial that gives like perspective, and then you can keep further expand this polynomial again and again and again, and we can even create huge polynomial or almost an infinite polynomial out of this. So the whole point of doing this to see the pattern of our polynomial with more accurate description, and then find our a. So imagine now we go back to our original p. Now it's going to be really big. Okay, earlier we had this, right? Remember? A plus. Okay, let me show you. Okay, remember here? We have px with a plus or these. Okay, and then look at the qx. Okay, we didn't know the qx in more detail until we did the LCM calculation to find the factor of a, and then plug in the right values to see that qx was this 42n plus x minus 2, x minus 6 rx, and then the rx could further be expanded to 28n plus all this. So let's just write them all in one equation. So a plus x minus 1, x minus 3, okay, remember this part was qx, right? this is qx, you see, qx equals 42n. Okay, let's write that down. 42n plus x minus 2, x minus 6, rx. Okay, now we can expand the rx, right? So I'm gonna erase that. Okay, let's write a different color. Okay, hopefully this makes sense to you guys. For qx, I'm gonna use red. 42n. Yeah, technically this should be a qx, but I'm gonna use rx to be different color. So now I have rx to be this 28n Okay, so now let's take a look at these numbers. Okay, earlier we set the a equals 315n, so we can replace that. So what's the least n we can have? Because we have all integers, we have to have all integer coefficient for each polynomial. We have to set x. We can set x equal m equals 1, and that's the least. Sure, we can have m equals 2, m equals 3. That's fine, but the least we can have is 1 to satisfy all 4 conditions we just created. Therefore, when m equals 1, let's go back to our a equation. There was 315 times m, right? Over here. Hopefully you can see this. A equals 315n. When m equals 1, our lowest we can have, a is just simply 315. Okay. And it asks for the smallest possible value of a. Answer has to be 315 here. Speed.